Hey all, I'm Manideep. I'm about to discuss today a quantum algorithm called Grover's quantum search. For the purpose of this video, I'll be referring chapter 6 of the book Quantum Computing and Quantum Information by Nelson and Chuang. Before we go and discuss what quantum search algorithm is, let us look at what a search problem is. In a search problem, you are given a finite sized input elements, say the set script x, which has x0, x1, so on till xn minus 1. This is of size n. And you are also given a function which is provided by an oracle, which behaves as f of x equals 1 only when x is equal to a certain xm, which is in the set script x, and is equal to 0 for all the x not equal to x. And the objective of the search problem is to find this xm, or simply the index m. Let's see how we can do that. The classical approach to do that using classical computing methods is by simply looking at every x in the script x set and substituting f of x and checking if it is equal to 1. You can substitute all the x's until you encounter an x such that f of x is equal to 1. On average, this will take n by 2 trials on average, and n trials in the worst case. The time complexity of the algorithm is therefore big O of n. Let's see if we can do anything better in an analogous quantum search algorithm. Okay, before that, if we look at quantum computation, the most important properties of quantum computation was we could achieve superposition, parallelism, entanglement, and interference. So we'll be looking to exploit these properties in order to design a better than big O of n search algorithm. And one such algorithm is the Grover's algorithm. Let us define again a quantum search problem. This is a search problem again, but in the quantum in which let's say we have inputs x0, x1, so until xn minus 1, all belonging to script x. This is the entire set script x, which is of size n. And let's say this set n, the size n is a power of 2. Capital N equals 2 power small n. And we index each element in this set by an integer from 0 to n minus 1. They can be binary represented they have a binary representation in small n bits. Let us generate a qubit representation for each of them, for each of these x, from 0 to n minus 1, all belonging to Hilbert space of 2 power n dimension size. In the classical case, the oracle provided simply directly with the function f of x. In this case, the oracle provides, say, with a unitary operator u of f, such that u subscript f applied on state x and an ancillary state y will be equal to x and y XOR f of x, where f is a function from the Hilbert space of 2 power n. F is a function from Hamming space of size 2 power n, Hamming space of size n, to Hamming space of size 1. And y is again another qubit which belongs to the Hilbert space of simple 2 power 1, the simple qubit. Now the way to go around this quantum search, Grover's quantum search algorithm has a few steps. We'll go step by step. If step 1, we generate a superposition state. That is more generally we start with the state 0, which is 0 0 0, all qubit 0. We pass it through a Hadamard gate, which is tensor product with n times. Hadamard, every qubit has a Hadamard product, and the output which we get would be a superposition state. That is, it's a superposition of all the states in this qubit space. It will be 1 by square root n summation over x, the qubit state x. Moving on, we'll go to step 2. Remember that the UF provided by the UF was provided by the oracle such that UF xy was equal to x y XOR f of x. We'll be using that UF unitary as unitary operator as a black box here. We'll pass the state psi, the superposition state we got, which was 1 by square root n times summation over x over this qubit state, and the output which we are going to get will be 1 by square root n times summation over x. Because there is a UF operator, we'll get x times y XOR f of x. Now in this case we'll choose y to be equal to the negative minus operator, which will be 0 minus 1 by root 2. This is the y which we'll be using. This is the ancillary state which we'll be using. We can generate this simply by passing 0 through the quantum state 1 through a Hadamard gate. And as seen in this box here, and as also been discussed in the earlier classes using Deutsch-Jozsa algorithm and the previous algorithms, this output when y is equal to -1 will be separable, and this the ancillary state will still be minus, and this state will be equal to, say, psi dash 1 by, which will be 1 by square root n summation over x minus 1 par f of x. Now the significance of this step is that we have separated the state xm, which gives f of xm equals -1 from the other states. Geometrically, what would happen is we have let's define alpha as the state xm and beta as the superposition of all the other states. There are n-1 other states, so 1 by square root n-1 summation over x not equal to xm x. This is the superposition of all the remaining states. And if I write psi as I expand psi this way, and I write sine theta by 2 and cos theta by 2, where I define theta as 2 times tan inverse 1 by square root -1, as shown in this diagram. Psi dash will be equal to minus sine theta by 2 plus cos theta by 2. That is, it will be a reflection in the beta axis, that is the x-axis here. It will be here psi dash. Now let's move ahead to step 3. In step 3, we pass the psi dash which we get initially. Now this is just the qubit state and no ancillary state. We just separated it. We pass it through this sequence of 3 gates, a H tensor n, and a phase gate, and again a H tensor n. If you look at this phase gate, it what it does is it's like a C minus operation. It keeps when the input state is 0, it keeps it as it is. When it is any other state, it'll just it'll just give a minus phase shift. So this will be this is this, if you go into the math, will be 2 times 0 0 0 0 bra 0 ket minus I. This is like a reflection in the 0 state. In the 0, if 0 state is a line in the Hilbert space, then this will be this unitary operator will be a reflection of the state preceding this unitary operation in the 0 state. Now if I combine all these three gates, H tensor n 2 0 0 minus I H tensor n, I'll be getting 2 times psi psi, because psi was the superposition state as you've seen in the step 1 as well. H tensor n times 0 will be equal to psi minus I. Now if 2 times 0 0 minus I was reflection in the 0 state, now this will be reflection in the psi state, and so the entire box is a reflection of psi dash, reflection of psi dash in state psi, and let's call this state phi. Now geometrically, if you look at it, psi dash was minus sine theta by 2 plus cos theta by 2 earlier, and because it's a reflection in psi, this psi dash subtends an angle theta, and thus it will reflect by an angle theta, and is now at subtends an angle 3 theta by 2 with the x-axis, and thus phi will be sine 3 theta by 2 alpha plus cos 3 theta by 2 beta. Now having done that, we moved successfully from state psi, which was here initially, to here after steps 2 and 3. Now what we do is we repeat these steps. We go back to step 2 and repeat it. Keep repeating them, say k times. If you look, step 2 was a reflection about the x-axis, and then step 3 was reflection about psi. After the first iteration of step 2 and 3, we got phi at an angle 3 theta by 2. If we go ahead and do a reflection with respect to x-axis, we're going to get a state over here, which will be at an angle minus 3 theta by 2. This will be, say, some phi dash, and now this will be reflected again in the phi, which is the blue line, and that will give a state which is at phi theta by 2 from the x-axis. So going on and on, after say k repetitions, we'll see that each state will subtend an angle 2k plus 1 by 2 times theta. So the state phi after k repetitions will just be sine of 2k plus 1 by 2 theta times alpha plus cos of 2k plus 1 by 2 theta times beta. Now say after k iterations, if we want the state phi, final state phi, to reach this state alpha, we'll see why that's important in a moment. If we want the state phi to reach the state alpha, we want the angle subtended to be close to pi by 2. That means 2k plus 1 by 2 theta should be close to pi by 2. That means k should be equal to pi by theta minus 1 into 1 by 2. And remember, theta was equal to 2 times tan inverse 1 by square root n minus 1 into 1 by 2 minus 1 into 1 by 2. Now this will give k, which is of this size, pi times square root n by 4. But we'll need a floor, or either a floor or a ceiling on this, because k is supposed to be an integer. It's the number of iterations, and then we'll go for the ceiling of the ceiling operator. And after those number of iterations, since phi has reached the y-axis, that means with very negligible probability it will take a state in beta. That means with very high probability it will just be a state alpha. And alpha is separable because it's a pure it's a pure state. It's alpha is of the form xm, which is of the form m0, m1, and so on till mn minus 1. So we just go and measure every bit of this output in the 0, 1 basis, and we get m0, m1, so on till m minus 1. And that's it. And if we go back and look at the cumulative circuit diagram, we started with the state 0, and then and get a superposition state, and then pass it through a block G. Let's call it a Grover's block. And a Grover's block is like this. It has the oracle given UF block, which gives a minus 1 power f of x here, minus 1 power f of x from the simple superposition. And now applying H tensor and phase gate and H tensor and again will give a state phi dash, which is now closer to the state alpha. And repeating this over pi times square root n minus 1 by 4 times the ceiling, we get close to pure state, which will be measured. Okay, now here's an let's write an algorithm for this. We have an oracle. The oracle gives UF such that UF times x y will just give x y XOR f of x, and we want to find an output x0. We start with an initial state psi, which is just the state 0. We get a superposition state by taking psi to be u, the Hadamard gate over psi. And now for k equals this number, the ceiling of pi times square root n minus 1 by 4 iterations, we do 2 steps. The first step is to apply the oracle operator. We take an ancillary bit minus and apply the oracle operator UF to get the particular psi, and we separate it. And after separating, we pass it through a sequence of H tensor n, then this reflection phase gate, and H tensor n times the earlier state psi. And after k such iterations, we measure the output qubit state of psi, and we return the measurement output x0, which will be m0, m1, so on till m, the bit representation of m0, m1, so on till m n minus 1. Now if you look at the time complexity, the first step takes constant time. The second step also takes constant time, and the third step takes each sub step in the third one takes just constant time. So the overall step takes k number of k iterations. So it will take big O of k, which is big O of square root of n. And measuring each output, there are log n qubits, so we measure log n qubits. So it'll just take big O of log n, and the resultant time complexity will be big O of square root n, which is a quadratic improvement over the classical method. Now the significance of this method, significance of the search algorithm is it can help solving some problems in NP. NP problems are those which can be verified in polynomial time given a solution, but can't be solved, but may or may not be solved in polynomial time. So if the domain of those inputs is a finite set of size n, we can just search for every input and just verify them, and verifying takes polynomial time, and that will just be big O square root n, big O of polynomial. If n is small enough, then this will be this problem is solvable. Okay. One error which may arise in the method we've discussed in the Grover's algorithm is if the final state phi after k steps, final step phi is not exactly coinciding with alpha. It can move around, it can be slightly off this y-axis, and we will see that this deviation can't be more than theta, because the angle is moving as 2k plus 1 by 2 times theta. So it at any step it can't have moved more than theta. So we can find a particular k where it stabilizes, where delta is less than equal to theta, and we'll call this angle with the y-axis delta. And theta was equal to 2 times tan inverse 1 by square root n minus 1. And the error in that case will be sine delta. That's the measurement output, and the probability that it will be something in beta, that will be sine delta, which will be close to delta, and which will be big O of 1 by root n. So with big O of 1 by square root n, we are able to solve search problem in big O of square root n time. That's it. Thank you.